Hello everyone, welcome to this presentation called Finite Volume Methods for Linear Hyperbolic Conservation Laws. My name is Hugo, and this presentation is part of a two-lecture series presentation that I'm offering in this channel. The first lecture was an introduction to these linear hyperbolic conservation laws, and this is the second part where I want to talk about the most popular methods used to solve this kind of systems, which are the finite volume method. I want to discuss basic schemes such as central, Lax-Friedrichs and Lax-Wendroff, and then I also want to give a quick introduction to the Upwind method, which is one of the most important methods, not only in hyperbolic conservation laws, but also in CFD. Then I want to finish the presentation with truncation, errors, and consistency, which are some tools that are used to evaluate the efficiency of these finite volume methods. The finite volume method used to solve conservation laws. I have already talked about this finite volume method in previous videos, but here is going to be slightly different. You will see why. But the idea is the same. For those of you that are not familiar with the finite volume method, do not worry. I will give a quick introduction to this method here. So the finite volume method is based on splitting your special domain into intervals. So let's say you might have a channel that has a length L. So you want to split the whole domain into smaller cells, which are called the finite volumes or the grid cells. So in the finite volume method, we want to obtain an approximation to the integral of Q over each of those volumes. So that means that, remember we have our whole domain that will be split into smaller cells. And in the finite volume method, we will be solving the hyperbolic conservation law in each of those cells. And in order to solve the hyperbolic conservation law in each of those cells, we need to approximate the solution Q. So that's why we will be using integrals. This will be clearer in a second. And in each time step, because we want to solve, we want to approximate the values of Q for every for a specific time interval. So in each time step, we will update the values of Q using an approximate value to the flux through the endpoints of the intervals. So this will be clearer with some images, but I want to give some quick introduction to some concepts. So each cell of our domain is going to be denoted by this Ci, which has these coordinates. For instance, let me put this here. So we have our domain. We are going to split this domain into 3 cells. So here, this cell in particular, which is Ci, which is the one that we specified in equation 23. So this cell contains a value of Q, capital QEI. You will see this, what is the meaning of this capital Q. But I just want to point out that this cell is going to be limited by these coordinates. This should be I. And then, as I was saying, in the finite volume method, we need to find the values of Q, because remember, Q is the solution of the linear hyperbolic system. So in the finite volume method, we will approximate using the average value of over the ith interval at time Tn. So that means that Q evaluated at this cell, evaluated at time n, is going to be equal to this average. Because if you remember my example from the beginning, in this limited domain, we might have some value of Q here at this coordinate, another one here, another one here, and so on. And you sum those values in this domain, and then you divide it over this delta x, which is the cell size, which is just the difference between these two coordinates, and this average is going to be equal to capital Q, which is the quantity that appears here. So yeah, in the finite volume method, we are going to obtain approximates of Q using average. And now, if somehow we know, if we know the value of Q at the time n, which is the value of Q at the time step Tn, the goal of the finite volume method is to estimate an approximate value at the next time step. So that means, and in the future. So that value at this time step t n plus 1 is going to be given by qi at the time n plus 1. So in order to derive this finite volume method, we need to integrate the linear conservation law, which is just the equation 10. Is this equation, a linear advection equation. So we integrate on this domain, on the spatial domain. So we have here our integral domain, or spatial integral, sorry. And then we have our temporal integral. Here it should be t. So we obtain these integrals over the linear advection equation. So we need to solve this integral in each of the cells of our domain. So these integrals can be solved really easily. We just need to split them and use the fundamental theorem of calculus. So this equation 25, becomes this equation. This equation can be easily obtained using algebra. I'm going to skip those steps, but you can do it by hand, and you will see that you end up with these equations that appear here. So we have the integral for q at time step n plus 1 minus the integral of q at time step n. So this has to be equal to a flux differencing. If you remember, this is the equation or the example that I showed at the very beginning. So we have some integral on the left hand side, and then some flux differencing in the right hand side. So remember, this integral on the right means that we have some changes over time of the quantity q that can change only due to this flux differencing. So now we also define this capital F, which is just an approximation to the average of the flux. So that means that F is just 1 divided by the time step multiplied by the integral from Tn to the new time step, and we evaluated this flux function here. So yeah, you can divide both sides of this equation by delta t and by L delta x, and then you can rearrange these equations to obtain equation 27, which is the finite volume method that we were looking for. So equation 27 tells us that the approximate value of q at this cell, evaluated at time step n plus 1, is going to be equal to the value of q at the same cell, evaluated at time n, minus this ratio between delta t and delta x multiplied by the flux difference. So that means the flow that enters the cell. So the flux that enters the cell is this one, and yeah, the flux that leaves the cell. So these fluxes are evaluated at these borders. Yeah, so that's why it appears as I plus 1 over 2, because the flux is being evaluated at this border, where the coordinate is xi plus 1 over 2. And yeah, the same applies for this flux that is evaluated at this border, whose coordinate is x I minus 1 over 2. So this, even though this equation is the equation we obtained, we cannot yet evaluate it because the true solution, the q value, varies with time. So that means that q is also going to be, q can vary here at these borders. And we don't have the exact solution to work with because, yeah, remember these f capitals are just the integrals of some function evaluated at q, but q is the exact solution, and we don't know the exact solution of the system. However, we can approximate these functions, these fluxes, based on the values of neighbor cells. So that means that, for instance, here, in order to evaluate this flux at this border, we can use the values of q from this cell and the values of q at this cell. And the same applies here. In order to approximate this flux, we can use the values of q from this cell and the values of q at the right cell. So that means that f at this border is a function that is going to depend on here the value of q here and the value of q to the right. And then the finite volume method, this equation 27, becomes equation 28. Here I forgot a parenthesis. So yeah, this equation 28 is an explicit method because it's yeah, it is an explicit method with a 3-point extension. So that means that in order to evaluate qi at the new time step, we need at least 3 values. The value of q at the cell center, the value of q to the left cell, and the value of q to the right cell. So yeah, so that's the meaning of 3-point extension. So once that we have specified these flux functions, we will have a fully discrete method. So this is another image that represents the finite volume method from equation 28. So yeah, we have the values of q at each cell. So we have some flux functions crossing the borders, and in order to evaluate the value of q at this cell but at the new time step, we need these 3 points and these 2 flux functions. So yeah, this is just a representation, a graphical representation of the finite volume method. So now let's present some finite volume schemes for linear hyperbolic conservation laws. So the simplest one is called the central scheme. So for this case, we will assume that the linear hyperbolic conservation law has a constant coefficients. That means that the velocity of the fluid is going to be constant. So the easiest way to approximate this function, this flux function, is using this equation, which is given by yeah, this is just an arithmetic average. So that means that we will sum the values from the cell to the right plus the value of q in the cell here, and divided over 2 and multiplied by the fluid velocity. So that's the flux function. The flux function at the right border here. The same applies to the flux function here. So now you will have an arithmetic average between this value and the value to the left cell. And then if you substitute these flux functions into equation 27, you end up with equation 30, which is yeah, the equation that allows us to obtain the value of q at cell I, evaluated at time step n plus 1. So yeah, So as I was saying, this scheme was derived using an arithmetic average between the values of Q and the values of Q at the left cell and at the right cell. Even though, although this method is very easy, this method is not recommended to use it because it's a very unstable method for hyperbolic problems. So I just included here because it's the simplest one, but I don't recommend to use it because your numerical simulations will exhibit instability. I'm sorry. Another much more better, or a slightly better finite volume scheme is the Lax-Friedrichs scheme, which intends to improve the stability of the central scheme. So yeah, the Lax-Friedrichs method will consider an arithmetic average of this value of Q that appears in equation 32. So this arithmetic average is just the value in the left cell plus the value at the right cell divided over 2. And then considering this, you obtain this equation. Here I forgot to include also a U bar here. But yeah, equation 33, oh no, yeah, it's fine, I'm sorry. This is the equation 33 is the equation for the flux function, which is given by this equation. And yeah, you substitute this equation into the finite volume method equation 27, and then you also obtain a flux function similarly for the for the left border, and if you substitute these equations into the finite volume equation, you end up with equation 34. And equation 34 is very similar to equation 32, but here we are considering the arithmetic average. So this scheme is slightly more stable compared to the central scheme. Now the Lax-Wendroff scheme. So this method is much more stable compared to the other two, because this method uses a Taylor series expansions to obtain second order accuracy for the solution Q. So I'm not going to do the maths, but in order to derive this scheme, you need to consider this relation that can be obtained from your linear hyperbolic advection equation. So Qt, the derivative of Q with respect to time, is going to be equal to this term, which is just this equation. Here you just move this term to the right hand side, and then if you are considering that relation, you can do some chain rule and then some other relations to end up with this equation, that the second derivative of the Q with respect to time is equal to U bar to the 2 multiplied by the second derivative of Q with respect to x. And then, yeah, you consider that Q is a smooth, then you can obtain a Taylor expansion for Q. And under those conditions, you can end up with this equation 35. This is the equation for the flux at the right border. Similarly, you can also obtain an equation for the left border. And then if you substitute these equations in equation 27, you end up with equation 36, which is a much more complete equation. You can see that in order to evaluate the value of Q at the new time step, you have more terms that you need to evaluate. You have this, here you have quadratic dependence on these terms. If you are familiar with CFD, you can some sort of recognize what this number is. I will be talking about this relation in a second, but yeah, this is equation 36 is the Lax-Wendroff scheme. So now let's talk about the Upwind method. So the Upwind method, the advantage is the following. The previous methods that I talked about, which were the Lax-Wendroff, the Lax-Friedrichs, and the central scheme, so those methods are center methods, and symmetric about the point where we are updating the solution. So we were just taking the cell here, and we just take the values from the left and from the right to evaluate Q at the new time step. But for hyperbolic problems, as we saw in the characteristics section, information is being propagated as waves move along characteristics. So you remember these equations that I was talking about. The solution Q propagates along these characteristics. So the solution Q is constant along these straight lines, and depending on the value of U bar, so the propagation can be, the information can be propagated from this direction to this one, and from this direction to this one. So the Upwind methods intend to use the knowledge we have about this information. For instance, direction of propagation, the direction from which this information is coming from. So using this information, we can design better numerical flux functions. And this is the idea behind the Upwind methods. So here I have some example. So here we have this graph. So in this vertical coordinate, we have the time coordinate at here at these cells. So we have some value of Q at this cell. So we have here this border, which is xi minus 1 over 2, and then we have this another cell that has value of Q evaluated at n. So these two cells are similar to these ones. So yeah, we have the left border, and we have the right border. So this is cell Ci. So in this figure, this is cell I, and here we have the x at I plus 1 over 2. So when the fluid velocity is greater than 0, in order to evaluate the value of Q at the new time step, so that means when the time step is n plus 1, so we can see that the characteristics are telling us that the information from the time step n is propagating in this direction. So that means that in order to evaluate Qi at the new time step, we will need information that is coming from here, from this cell and from this cell. But it's the opposite. Well, what happens when we have the opposite case? When here it should be smaller than 0. I'm sorry again. So at the right border, when you want to evaluate Q at cell I at time step n plus 1, you will need information that is coming from here, from where the value of Q at this cell is Q at I plus 1. Now for the scalar advection equation, as we know, there is only one speed, which is the fluid velocity U bar, which can be either positive or negative. So the Upwind is considered to be a one-sided method, with the velocity at the cell I evaluated at the new time step n plus 1 is determined based on values only to the left or only to the right. So in figure 6, which is this figure I showed before, so we illustrate how the information in a given cell propagates from the old time step to the new time step. So here, for instance, here this line represents the values of Q evaluated at time step n plus 1, and here this line, this horizontal line, represents the values of Q being evaluated at Q, the values of Q evaluated at time n. So we can see that here, to obtain the values at the new time step, we need information from these cells, from the values of Q at these cells. More specifically, for instance, for the when the fluid velocity is positive, the flux at this border depends only on Q, because we know that the information is coming from here. So here we want to evaluate the flux here, so we know that we need information from this value of Q at y minus 1. On the other hand, the flux at here, when the velocity, the fluid velocity is negative, remember here I made a mistake, but now we want to evaluate the values of the flux at this border at here. We know we must need information from that is coming from this cell, from this value of Q, which is Q at I plus 1. So yeah, this is when the fluid velocity is negative. So these relations, this information can be assembled into this piecewise numerical flux, which can be computed as in equation 37. So the flux, remember, the flux here at this border is going to depend on the value of the fluid velocity. So when this fluid velocity is greater than 0, so that means we are here. In this case, remember, at this border represents the coordinate xi plus 1 over 2. So when we have this condition, the flux will adopt this value, which is the fluid velocity, multiplied by this value of Q evaluated at time step n at cell I, because yeah, the information is coming from this cell at this border. So yeah, we need this value of Q in order to evaluate the flux at that position. But on the other hand, if the fluid velocity is smaller than 0, so that means we are in this case at here. So in order to evaluate the flux here, we need the information from the cell, and more specifically the value of Q at the cell I plus 1, which is yeah, this equation. So now we have the complete information about the flux function, so we can compute using equation 27. We can compute now the value of Q at the cell I at the new time step n plus 1, which is given by equation 38. So this equation, we have equation 38 and equation 39 depending on the value of the fluid velocity. So for the when the fluid velocity is positive, Q n plus 1 needs the values of Q at the cell I and Q at the left cell, which is this one. But when the fluid velocity is negative, in order to evaluate the value of Q at the new time step, we need the values of Q at the right cell, which is this one, and the values of Qi at the cell we are solving the equation, which is Qin. So this Upwind method can also be analyzed, can also be studied from a wave propagation waypoint. Remember, in the previous presentation, we saw that the solutions of the linear advection equation take the form of waves being propagated from one direction to another one. So these equations, these jump functions, which are just differences between the values of Q. For instance, this jump function evaluated at here at this border is just, or at this border, this difference is just the value of Q at the right cell minus the value of Q at the cell in the middle, which is just this difference, this value minus this value, and Q and W at the left border, it will be at this one. So the jump function here is just the difference between the value at this cell minus the value at the value of Q in the left cell. So you will see why these jump functions are important, but I just want to to say that these jump functions represent the waves that are moving towards the cells to the right, and the cell in the center with velocity u bar. Thus, the finite volume equations, the finite volume conservation law equations 38 and 39, in terms of these jump functions, adopt the form of equations 41 and 42, where you can see here that the jump function appear here. This one appears here when the fluid velocity is greater than 0, and when the fluid velocity is smaller than 0, we have this jump function here. So these jump functions are important because Q, we have our geometry here, we have our cells. So Q, the values of Q adopt piecewise functions. So for instance, they also exhibit discontinuities at the borders. So for instance, we have the left cell here, the cell in the middle here, and the cell in the right has these values. So here we can see that we have discontinuities at the borders. So the jump functions actually represent these discontinuities. So that's why they are relevant. And here, this is the bottom pair of graphs shows the data at time n, which are represented as a piecewise constant function. And we can see that the discontinuity that is being originated at this border x I minus 1 over 2, this discontinuity can be seen as this wave. For instance, for this case, we have this discontinuity represented by this jump function, this one here as this jump function, and so on. And we have the case where the fluid velocity is greater than 0 and the fluid velocity is smaller than 0. And here we have the values of Q at the new time step. So you can see that here this discontinuity that initially appeared here now is being propagated here. So the jump function will tell us where this discontinuity is now being displaced. Now the discontinuity that was here now appears here. So also the jump function tells us where this discontinuity will be, and the same here. The discontinuity that was here now appears here. So it's similar to the case when the fluid velocity is smaller than 0. So that's why these equations are also important, because these equations allow you to see these discontinuities, how these discontinuities are being propagated from one direction to another one. Also, this is just to simplify these equations, which can be a bit messy. So you can define the flux as this with equation 43, where U positive is just the max value between U bar and 0, and U negative is just the minimum between U bar and 0. So this is the general equation of the Upwind method. So this equation can be simplified to the equations 38 and 39, and equation 41 and 42. So so I also want to quickly discuss the Courant-Friedrichs-Lewy condition, or CFL, which is a necessary, or the majority of the cases, it's a necessary condition to guarantee convergence of the finite volume methods for solving hyperbolic partial differential equations. I'm not going to show the maths behind the derivation of this CFL condition, but it arises in the numerical analysis of explicit time integration schemes. So as you can notice that the majority of the schemes that I presented here, for instance, this one 44 for the Lax-Friedrichs, equation 34, equation 36 for the Lax-Wendroff, all these equations are explicit schemes. That means that in order to evaluate the value of Q at a new time step, we only need information from the previous time step. In the implicit case, it will be a bit different. In order to evaluate Q at a new time step, you might have also values of Q, for instance, Q at the right cell or at the left cell, but evaluated at a new time step. So for the implicit scheme, you will end up with a matrix system, a linear metric system that can be solved using numerical techniques. But this is not just the case. The finite volume methods schemes that I presented here are explicit time integration schemes. So this Courant-Friedrichs-Lewy condition applies for these schemes. And yeah, one of the main important results from the CFL condition is that it says that the time step must be less than a certain upper bound given a fixed special increment. Otherwise, the simulation produces unstable results. So this is observed when this Courant number, which is small c is defined as this product between the fluid velocity multiplied by delta t divided over delta x. This ratio has to be smaller or equal than 1. If this condition is not satisfied, the numerical schemes that we presented before are going to be unstable. So you want to avoid instability. So in order to guarantee stability of your finite volume method schemes, this Courant number has to be smaller, much more smaller than 1. So this number actually appears here, as you can see in equation 44. Also for the Lax-Wendroff appears here. Here the Courant number is actually c to the 2. So the Lax-Wendroff method has a quadratic dependence on the Courant number. For the Lax-Friedrichs, it appears here, and also even for the central scheme. So that's why this is one of the reasons why the central scheme is unstable, because you cannot guarantee stability even if the Courant number is smaller than 1. It has to do with stability. You will have to do Van Neumann stability analysis, but this is something I will not discuss here. But yeah, just to conclude, local truncation error. So these truncation errors are also important to analyze the consistency of your numerical method. So for instance, for an explicit numerical method, any explicit numerical method can be written as equation 46, where this C, bold C, evaluated at the new time step is equal to some numerical operator that depends on the value of C at the time step n. So you can see the explicit schemes that we showed before all adopt this form, where all the right hand side is given by this n. So in order to evaluate the value of your solution at the new time step, you need to apply this numerical operator to the values of C at time step n, which is what we are doing in this Upwind method. So this is the numerical operator for the case of the Upwind method. For the case of Lax-Wendroff scheme, the numerical operator is all this right hand side of equation 36, and so on. So yeah, so this numerical operator represents n represents the numerical operator that approximates the solution at the new time step t n plus 1. So the local truncation error, which is given by this tau evaluated at time step n, is the error made when you insert the exact solution into the proposed numerical scheme. So let's say that you somehow have the exact solution to your linear advection equation. And then if you introduce that exact solution into the numerical scheme, the explicit numerical method, you will obtain this n evaluated at a small c. And then if you obtain the difference with respect to the true solution, the exact solution at the time step n plus 1, if you obtain this difference and then you divide it over delta t, you obtain the local truncation error. Yeah, I was saying that Cn is the vector with the exact solution. So we define consistency as a finite volume method is considered consistent that if by reducing the mesh and the step size, the truncation error terms could be made to approach zero. So that means you, in any finite volume method or in any numerical method, you want the local truncation errors to be zero as much as possible, or as small. You want your local truncation errors to be as small as possible. If you satisfy this condition, you will have a consistent method, because the exact solution will the numerical method that you are using, it can be either Upwind method, it can be Lax-Wendroff. You evaluate that operator using the exact solution, and if you obtain the difference with respect to the exact solution, and if that difference is equal to zero, that means that your numerical method is great, it's consistent. So you want to achieve that. So some exercises that I included here. I'm not going to do the maths, but we consider the Upwind method for the advection equation with constant velocity. So this is equation 48 for the case where the fluid velocity is greater than zero. So you applied this method to the exact solution. Let's say you have somehow the exact solution to the linear advection equation, and then if you substitute this exact solution into this scheme 48, and if you obtain the difference with respect to the exact solution, you obtain equation 49. So you can some sort of approximate these terms, the ones that appear here and the one that appears here, and then you use Taylor series, and then you obtain the differences between all these terms, and then you will end up with this equation 50, which is the local truncation error for the Upwind method. So you can see that the truncation error is not exactly zero, because it will have some terms. So you will have a term that is going to be dependent on the cell size of your mesh. So you will also have some dependence on the Courant number and a dependence on the second spatial derivative of Q. So remember the definition of consistency. If you somehow manage to reduce the mesh, so let's say delta x is very small, so you have very small cells. So that means if you have very small cells, so that means that this term is going to be almost zero. So remember that if you can make the local truncation error to approach zero, your finite volume method is going to be consistent. So for the case of the Upwind method, this method is consistent of order 1, which is the order of the leading order term of the local truncation error for the Upwind method. So here we have a dependence on delta x to the 1. So the superscript of this delta x is 1, so that means that superscript, the power law of this superscript, the power law of this delta x is 1, so the consistency, the order of consistency of the numerical method is 1. So yeah, we also have some terms of order delta t to the 2 that we are not considering. But yeah, so the message is this one. So the Upwind method can be is consistent if delta x can, if you have a cell size, a very small cell size. Now for the case of the Lax-Friedrichs and Lax-Wendroff method, in order to obtain the local truncation errors for these methods, we have to respect the CFL condition. So that means that the Courant number has to be smaller or equal to 1. So we consider the worst case scenario when delta, if we assume that the fluid velocity is equal to 1, delta t is going to be approximately similar, the value of delta t is similar to the value of delta x. So this is what we consider here. So assuming that the local truncation errors for the Lax-Friedrichs is equation 51, so you can see that we also have a dependence on delta x, dependence on the Courant number, and a dependence on the second derivative of q with respect x, the second derivative, and we have 1 over 2 multiplied by the fluid velocity. So once again, this method is consistent of order 1 for delta t or for delta x. So remember, the order of consistency of the method is the superscript of the delta x. So so delta x, the superscript of delta x is 1, or the power law of the delta x is equal to 1. So that means that the order of consistency of this method is 1. For the Lax-Wendroff method, we have a slightly different equation. So the local truncation now also it also depends on the Courant number, but we can see that we have a quadratic dependence on the Courant number and a quadratic dependence on delta x. So this superscript is the order of consistency of the method. So in this case is 2. So the higher the order of consistency of the method, the better, because if delta x is small, delta x to the 2 is even smaller. So under these conditions, it's much easier to make the local truncation error approach 0. We also have a fourth derivative of q with respect to the position. And remember that I said that the Lax-Wendroff method is very stable or very consistent, or is a much more better scheme compared to the Lax-Friedrichs and the central scheme, is because of this, because the local truncation error can approach 0 if we have a smaller cell size. So just final comments about this lecture series. So in the first lecture, we gave a quick introduction to hyperbolic conservation equations, and these equations are relevant because they can be used to track the concentration of a contaminant in a river, but it can also be used in any other kind of systems that involve transport by advection of a particle. The finite volume methods are the most efficient numerical methods to solve these kinds of equations. In the previous presentation, we also discussed very quickly how the finite difference method failed to solve hyperbolic conservation laws with discontinuities in the initial conditions. The finite volume method, the main advantage is that it allows you to impose discontinuities in the initial conditions for this kind of systems. In this presentation, we particularly discussed we gave a quick introduction to methods, finite volume methods that can be used to solve linear scalar hyperbolic conservation laws, such as central, Lax-Friedrichs, Lax-Wendroff, and the Upwind methods. And we saw in the previous slide that the Lax-Wendroff is consistent of order 2. It's a really good scheme, but the Upwind method has much more relevant physical meaning, because of the Upwind methods allows you to obtain important physical information from the system using characteristics. We know that information can be propagated from one side to another one. So the Upwind methods consider that information. The Upwind methods consider direction of propagation and the direction from which this information is coming. So and we did not discuss here. We only focus on talking about linear advection equation, and very simple hyperbolic PDE, but there are much more complex PDEs. For instance, I gave a quick introduction to this system of hyperbolic conservation laws. So yeah, these equations are, as I said before, these equations consist of vector quantities, and also instead of a fluid velocity here, you have a matrix of velocities. So yeah, we did not discuss those PDEs, but there are multiple methods that can be used to solve this system of hyperbolic conservation laws, such as the Riemann problem, the Godunov method. So you can find plenty of information in the literature about these methods. So in the future, if someone is interested in studying these systems, and if you want me to give or to make a presentation about those numerical methods for those system of hyperbolic conservation laws, I will be happy to do it, but let me know if you will be interested. So just to conclude the presentation, the main reference for this in making this presentation is the book of Lebesgue, which is the main source of linear hyperbolic conservation laws. So I highly recommend this book. It's really good. So the information I presented here is a summarized version of what you can find in the book. So thank you everyone for being here and for watching this video, and until the next time.